here is another example. Given this function, find and classify any stationary points. So the first step is to determine the first derivative. So step 1, determine the first derivative. Okay, we had already calculated this previously, so I'll just state it here. The first derivative is 6x over x squared minus 1 squared, and this was calculated in the previous video. Okay, step 2, we need to find the critical points. So step 2, find the critical points. And these are the points where f dash x equals to 0. Yeah, the points where f dash x is equals to 0, or where it does not exist, all right? Where f dash x, or where the derivative does not exist. Okay, and basically these are points where a function is discontinuous, so that is basically vertical asymptote in this case. Okay, now we had already calculated this previously, and our critical points were x equals to 1, x is equals to -1, and x is equals to 0. So I'll just add another note that this was calculated in previous videos. Okay. Step 3, we need to evaluate the derivative between or either side of the critical points. Now you have to be careful with that because some critical points are asymptotes, but I'll show you what to do. So step 3 evaluates the derivative between or on either side of the critical points. Okay, so what that means is we need to draw a sign diagram. Okay, we need to draw a sign diagram for these guys here. We had already done this previously again. So we have 0, we have 1, we have -1. And what you're interested in, by the way, these are x values. What you're interested in is the sign of the first derivative. And we picked test points, okay? We picked test points on each of these sides. So here we picked f dash -2, and it was -4/3. Here we picked f dash -0.5, and it was -16/3. Here we picked f dash 0.5, which was 16/3. And here we picked f dash 2, which was 4/3. So we looked at the signs and we said here it's negative, here it's negative, here it's positive, and it's positive here as well. But we said that this is an asymptote, so it cannot be a maximum or a minimum, and this is also an asymptote. Okay, it's not a maximum or a minimum. So the only point that we'll be looking at here is 0. Now, of course, if we look at 0 here, we can see that at 0, we are basically going downhill and uphill, which means that's a minimum point. So we can go ahead to step 5 step 4 and test the critical points. Of course, you know this is a minimum point, so we can just go ahead and state it. So in step 4, where we need to test the critical points for maxima or minimum, we can just go ahead and say, well, by looking at that point, and we've just looked at it from above there, we can see that at x equals to 0, the slope changes from negative to positive, okay? Which means this is a minimum point. So in step 5, all that we have to do is to calculate the y coordinate and we'll be done. So step 5, find the y coordinate. So, and all that we have to do is to plug 0 into the original function, okay? If you plug 0 into the original function, the value of y will be 4, sorry. So we can go ahead and say 0, 4 is the minimum point. Okay. Here's another example. Given that f of x is equals to x cubed, find and classify any stationary point. So the first step again is to determine the derivative. So step 1, determine the derivative f dash x, and we can see that f dash x here is 3x squared. In fact, we calculated this previously. Step 2, we need to find the critical points. And these are the points where f dash x is equals to 0. So, which means we just need to equate our first derivative to be equal to 0, and x equals to 0 is our critical point. We had already done that previously as well. So step 3, we need to evaluate the value of the gradient on each side of that point. So evaluate the derivative or the slope on either side of the critical point. Which means we draw a sign diagram for this for values of x. Now here we have 0. We are interested in the signs of the slope, so we pick test points. Here we picked f dash negative 1, which was 3, f dash 1, which was 3 as well. And we said, well, here it's positive and here it's positive. Okay. So what does this imply? So it means that at x equals to 0, this function does not change sign. So this function has no local maximum or minimum. Okay, so we can just go ahead and write this conclusion. All right. So at x equals to 0, f dash x, or the slope, does not change. does not change sign, which means that the original function f of x, the original function um, has no local maximum or minimum. So has no local maximum or minimum.